You type 3 letters into a search bar, and before you even finish the word, a list of suggestions appears. Apple, application, append, approach, all of them matching what you've typed so far. This happens instantly, not in a second, not in half a second, in under a millisecond. And the dictionary behind that search bar might contain 250,000 words or more. So how does the system find every word starting with those 3 letters, out of 250,000 entries, faster than you can blink? The brute force answer would be to check every single word. But that's clearly too slow at this scale. There must be a smarter approach. The answer is a data structure called a trie. It's specifically designed for exactly this kind of problem, finding words by their prefixes. And by the end of this video, you'll understand exactly how it works, step by step. Let's start with the obvious approach. You have a list of words, and you want to find every word that starts with a given prefix. The simplest solution is to loop through every word in the list and check if it begins with your prefix. Compare character by character. Does the first letter match? The second? The third? For a small dictionary, say 100 words, this is perfectly fine. But what happens when your dictionary grows to 250,000 entries? Now you're comparing your prefix against every single word. That's O of n times m, where n is the number of words and m is the prefix length. For each word, you potentially check m characters before deciding it doesn't match. As the dictionary grows, search time grows linearly with it. 1,000,000 words means 1,000,000 comparisons. 10 million means 10 million comparisons. We need a data structure where the search time depends only on the length of the word we're looking for, not on the size of the dictionary. A trie, short for retrieval and pronounced trie, is a tree-shaped data structure built specifically for storing and searching strings. Here's the key idea. Instead of storing each word separately, words that share a common prefix share the same path from the root of the tree. Let's build one. We start with an empty root node. Now let's add the word cat. We create a path, root to C, C to A to T, and we mark the T node to indicate that a complete word ends here. Now let's add car. We start at the root, follow C, then A. Both of these nodes already exist. But at A, there's no child for R, so we create one, and we mark R as an end-of-word node. Next, card, we follow C, A, R all exist, then we create D and mark it. Finally, care. We follow C, A, R again, then create E and mark it. Notice how the prefix CA is stored exactly once, even though 4 words share it. This shared structure is what makes tries so powerful. Let's look at the insertion algorithm more carefully. Suppose we have a trie that already contains cat and car, and we want to insert the word cup. We begin at the root node and look at the first character. See, the root already has a child for C, so we follow that existing edge. No new node needed. Next character, U. We're now at the C node, and we check if it has a child for U. It doesn't. So we create a brand new node for U and add an edge from C to U. Next character, P. We're at the U node, and there's no child for P, so we create another new node for P, add the edge, and since P is the last character, we mark it as an end of word. That's the entire algorithm. For each character in the word, check if the current node has a child for that character. If yes, follow it. If no, create it. After the last character, set the end of word flag. The time complexity is O of m, where m is the length of the word. Every insertion touches exactly m nodes, regardless of how many words are already in the trie. Searching a trie is almost identical to insertion, except we never create new nodes. Let's try 3 different searches to see the possible outcomes. First, let's search for car. Start at the root. Follow C, then A, then R. We successfully reach the R node, and it's marked as an end of word. So car is in our trie, found. Now let's search for ca. Start at root, follow C, then A. We reach the node successfully. But here's the thing, A is not marked as an end of word. The path exists, but ca was never inserted as a complete word. It's just a prefix, not found. Finally, let's search for cow. Start at root, follow C. Good so far. Now we need O, but the C node has no child for O. We've hit a dead end, not found. In all 3 cases, notice something important. We never looked at any other word in the trie. We followed exactly one path, checking one character at a time. The search is O of M, where M is the length of the word, completely independent of dictionary size. This is where tries truly shine. Prefix search is the operation that powers autocomplete, and no other common data structure does it this efficiently. Let's say we want to find every word that starts with car. Step 1. Navigate to the prefix node. Follow C, then A, then R. This takes O of M time, where M is the prefix length. Step 2. From the R node, explore every path below it. This is just a depth-first traversal of the subtree rooted at R. Every node we encounter that's marked as an end of word is a result. Starting at R, it's an end of word itself, so car is a result. Follow the edge to D, that's an end of word, so card is a result. Back up to R, follow the edge to E, end of word. Care is a result. We found 3 matches by traversing just the relevant subtree. We never touched cat or cup or any other word that doesn't share the prefix. The total time is O of M plus K, where M is the prefix length and K is the number of matching results. Remember the search bar from the beginning? This is exactly what's happening under the hood every time you type. Removing a word from a trie is a bit more nuanced than insertion. We can't just delete nodes blindly, because other words might depend on them. Let's delete card from our trie. First, we navigate to the last node of the word. Following C, R, D, we unmark D as an end of word. Now card is no longer recognized as a complete word. But we're not done yet. We need to clean up. The D node currently has no children and is no longer an end of word. It's completely useless, so we remove it. Now we check its parent, the R node. Does R have any remaining children? Yes, it still has an edge to E because care is still in the trie, and R itself is an end of word for car, so we leave R alone. That's the cleanup rule. After unmarking end of word, walk back up the tree. At each node, if it has no children and is not an end of word, remove it. Stop as soon as you hit a node that should stay. Deletion, like everything else in a trie, is O of M, where M is the word length. Let's put it all together. In a trie, insertion is O of M, search is O of M, deletion is O of M, prefix search is O of M plus K in every case. M is the length of the word, and K is the number of results. The dictionary could have 100 words or 100 million. The time for any single operation stays the same. It depends only on the word, never on the collection size. Compare this to the brute force approach at O of N times M, where N is the dictionary size. That's a massive improvement. But there's a trade-off: space. Each node in a basic trie can have up to 26 children for English lowercase letters. Most of those slots will be empty, meaning we're allocating memory for pointers that point to nothing. For dense dictionaries where many words share prefixes, tries are very space efficient because of prefix sharing. But for sparse data with little prefix overlap, a trie can use significantly more memory than a simple list. There are optimized variants like the Patricia trie and the ternary search tree that reduce this overhead. But the basic trie remains the clearest way to understand the core concept. Tries are everywhere in the software you use every day, often hiding behind the scenes. Let's look at 4 major applications. First, autocomplete. Search engines, code editors, and your phone keyboard all use tries or trie-based structures to instantly suggest words as you type. Every keystroke narrows the search to a smaller subtree. Second, spell checking. When you type a misspelled word, the spell checker searches for words in the trie that are close to what you typed, using techniques like edit distance combined with trie traversal. The trie makes it fast to explore similar words. Third, IP routing. Network routers use a specialized form of tries to perform longest prefix matching on IP addresses. When a packet arrives, the router walks its trie to find the most specific route that matches the destination address. Fourth, bioinformatics. DNA sequences are strings over a 4-letter alphabet. A, T, C, and G tries help match query sequences against massive genomic databases efficiently, since DNA data has enormous amounts of shared prefixes. Whenever your problem involves searching, matching, or completing strings by their prefixes, a trie is likely the right tool for the job. Let's close by comparing tries with two other common data structures: hash tables and balanced binary search trees. Hash tables are the gold standard for exact lookups. Given a key, you get the value in O of 1 average time. But hash tables can't do prefix search at all. If you want every word starting with app, a hash table gives you no way to find them without scanning every entry. Balanced binary search trees like red-black trees or AVL trees keep their keys in sorted order. You can do range queries and iterate in alphabetical order. But finding all keys with a given prefix requires navigating to the range start and scanning, which is less efficient than a tries subtree traversal. Tries excel specifically when your operations involve prefixes, shared beginnings, or you need to enumerate completions. Their O of M lookup is independent of collection size, and prefix search is a natural, built-in operation, not an afterthought. The takeaway is simple. Choose the data structure that matches your access pattern. For exact lookups, a hash table. For sorted data, a balanced tree. And for anything involving prefixes, the trie is king. That's how tries actually work. Thanks for watching.